At the beginning of this chapter, we said that we use capacitors to store energy to use at a later time. So the natural question now is, how much energy do we store in a capacitor? And to answer that question, I think we should remember the concept of potential energy. Imagine that you have a bunch of charges as seen here. So I have four stationary charges, and I'm going to move this charge from this point to, let's say, to this point. And while I'm moving that, obviously I'm going to do some work on it. And this work that I will do will be equal to the change in the potential energy of the system, which we write it as the work that I will do is the change in the energy of the system. I guess maybe I can write here, right? This is the work that I will do, which is the moving charge times the change in potential. And this change in potential is actually the potential difference between point B and point A created by the remaining four charges. So I'm going to make use of the same idea here. Now consider that we have a parallel plate capacitor such as this one. Now imagine these plates already have some charges on them. So this plate has positive Q and this plate has negative Q on it. And you know that when there is charge on the plates, there is a potential difference between the plates, and this potential difference is called delta V is equal to V. So these Q and minus Q are like our stationary charges here. What I'm going to do is I'm going to take a tiny bit of charge from the negatively charged plate, dq, and I'm going to move it to the positively charged plate. So how much work will I do, or how much change will occur in the potential energy of the system is actually quite simple. Now I know the answer. du is equal to the moving charge, which is dq here, times the potential difference the charge goes through, which is the potential difference between the plates, so dq times v here. And to find the total potential energy stored in a capacitor, what I should do is I should start with zero charge on these capacitors, and I should fully charge it 1 dq at a time. And every single time I should calculate the change in the potential energy, and I should add them up until it is fully charged. So all I need to do is an integral. So the change in the potential energy delta U, which is going to be the potential energy when it is fully charged, minus the potential energy when there is no charge on these plates, which is going to be 0, is equal to dq times v. And the limits of this integral should be, since it's an integral with respect to q, from 0 charge to the charge on the capacitor when it is fully charged. Now this v changes with the charge on the capacitor, so I cannot simply take it out of the integral. So what we should do maybe is to express this v as a function of q. But lucky for us, we have the capacitor equation, which relates the charge on it to the voltage across its plates. So we can make use of this expression to express voltage as a function of Q, which is Q over C. Now all we have to do is take this guy, put it in the integral, and we will have our potential energy. So U is going to be equal to, from 0 to Q, Q over C dq. Now unlike the potential, the capacitance of a capacitor is constant unless you change its dimensions, which we are not gonna, obviously. So this is going to be equal to then 1 over c. We took the constant out. In the integral we have q dq left, and the integral of q is nothing but q squared over 2, and the limits were from 0 to q. So if you solve this, we are going to find the potential energy stored in a capacitor to be 1/2 q squared over c. So we found the potential energy stored in a capacitor as a function of its charge and the capacitance. But what you can do is you can also make use of the capacitor equation to express the potential energy stored in a capacitor as a function of V and C or V and Q. Because I know that Q is equal to C times V, right? So if you plug in C times V here, one of the C's will cancel out, and you are going to get 1/2 CV squared. Or you can express one of the Q's as C times V, and the C's will cancel out, and you'll be left with V times Q. And as you all remember, the energy unit is joules. One thing to note here is that it was us who brought one dq at a time from one plate to the other so that we store some potential energy, but in a given circuit this work will be done by the battery. Okay, now with that note out of the way, let's solve some examples. In this problem, we need to find the energy stored in a camera flash capacitor if it was connected to a 200 volt battery and has a capacitance of 150 microfarads. Now this is part A, and in part B the question is to calculate the power output if all of this energy is released in 1 milliseconds. Now for the energy stored in a capacitor we have three expressions. Now which one you use obviously depends on the problem that you face. Whichever makes the solution easier, just pick that one. Now in this problem what are given to us is the capacitance and the voltage across the capacitor. So I guess we could make use of the second expression over here. So that's what I'm gonna do. So U is equal to 1/2 C times V squared, which is going to be equal to 1/2. Now 150 microfarads, remember I always need to use the SI unit, so it's going to be 150 times 10 to the minus 6 farads, and I need to multiply this with 200 volts squared. So if you calculate that, this is going to give us an energy of 3 joules. So apparently in this capacitor, when it is connected to 200 volts, an energy of 3 joules is stored. Now in part B, the question was to calculate the power, and if you remember from Physics 101, we defined the power as the rate at which the work is done or the rate at which the energy is changing. So I'm going to make use of the second definition here. So the average power is going to be equal to the change in energy divided by the time it takes to have that much change. And in this case, the energy is the energy stored in the capacitor. So I'm going to have delta U divided by time. We started with this much energy and all of it is released. So we are going to have 3 joules divided by 1 milliseconds, and milliseconds is basically 1 times 10 to the minus 3 seconds, and this is going to give us an average power output of 3000 watts or 3 kilowatts. Just to have a reference and to see how small or a big of a power this is, why don't you guys compare this to the power of some of the home appliances you might have at home, like a vacuum cleaner or a heater. Alright, so with this we conclude this example. Let's move on to the next one. In this problem, we first charge a parallel plate capacitor using a battery. When it is fully charged, it has a charge of Q and voltage V0 on it. And apparently once it is fully charged, we disconnect it from the battery and increase the separation between the plates from D to 3D. And the question is, how will the energy stored in the capacitor change? Will it increase, will it decrease, or will it remain the same? And if it does change, find the new energy. Since it was disconnected from the battery and we are not affecting the charge on the plates, in its final state, the capacitor will still have the same charge on the plates. Now, what about the voltage? Well, I don't know. Probably it will change as well. We will see how it will change in a moment. I will start with the fully charged capacitor before we do anything to it. Now, since this is a parallel plate capacitor with an area A and the separation distance D, the original capacitance is equal to epsilon 0 A over D, and the energy, let's say, stored in this fully charged capacitor is 1/2. Now, there are three different expressions that we can use, but since I know that the charge doesn't change on the capacitor in its initial and final state, I'm going to use Q squared over C. In this case, it will be C0. And V0 is equal to, from our capacitor equation, Q over C0. Now let's have a look what happens in the final state. Now I'm going to call the new capacitance C, which is going to be from the parallel plate capacitance equation. It's going to be epsilon 0 A over the distance between the plates. Now the distance is 3D, which is, by the way, if you pay attention, 1/3 of the original capacitance. So apparently by increasing the distance from D to 3D, we decrease the capacitance by a factor of 3. Alright, now that we know the new capacitance, we can calculate the new energy. The new energy is, again, I'm going to make use of the same expression, 1/2 Q squared over C, which is going to be 1/2 Q squared over, now C is equal to C0 over 3, C0 over 3. You can take this 3 up, which is going to give you that the new energy is actually nothing but 3 times the initial energy. So apparently by increasing the distance by a factor of 3, you increase the energy by a factor of 3. Now let's see if the voltage changes. I know this is not part of the question, but let's have a look at it anyway. The final voltage from the capacitor equation is Q over C, which is going to be Q over C0 over 3, which is going to be 3 times V0. As you can see, the voltage between the plates increases by a factor of 3 while we are at it. Maybe what I should do is, I should ask you, how would the electric field between the plates change? Now, we know that this should be equal to E0 times D. And if you solve this for E0, what you are going to find is E0 is equal to V0 over D. Now let's have a look at the electric field in the final state. Now I know that voltage is equal to the electric field times the distance between the plates. In this case, the distance is 3D. And if you solve this for the electric field, what you are going to get is 3V0 divided by 3D is again V0 over D. So apparently the electric field does not change. Having the same electric field makes sense because if D is really small compared to the dimensions of these plates, probably 3D will also be very small compared to the dimensions of these plates. So the electric field will still be equal to sigma over epsilon 0, which is constant, by the way. All right. So we answered more than what was asked in the question, and actually I have one more question in my mind to discuss before I move on to the next subject, which is related to the work done on this capacitor. Now we found that the energy stored in this capacitor increased by a factor of 3. It means that the work that we did to increase this distance must be positive. Is it? Now, to answer that question, maybe what we should do is, let's say this positively charged plate is fixed in its position and we are going to move the negatively charged plate in this direction. Now, you have a positive Q here, you have a negative Q here, meaning this positive Q will apply a force on the negative Q in which direction? Towards itself, right? So we need to overcome that force to increase the distance between them, to pull this plate in the opposite direction. So this is the direction of the force that I need to apply, and the displacement is also along the same direction, which means that the work that I will do is positive. That is why the energy stored in this capacitor increases. So maybe as a homework problem, you can calculate exactly how much work we did. Great. Not only did we answer more than the question asked for, but also you got a homework out of it. And actually, there's another homework for you. In this problem, you are going to do the same thing while the capacitor is still connected to the battery. Even though this seems like a very small detail, it will change quite a lot. So you try to solve this, and eventually I will try to post the solutions to these homework problems. Now let's talk about energy density. The energy density is nothing but energy per unit volume, and to define it, let's first consider a parallel plate capacitor. Now, if a parallel plate capacitor has a charge Q on it, if you know the voltage across it, you know that the energy stored on this capacitor is nothing but 1/2 times C times V squared. Now, I know what C is for parallel plate capacitor, which is epsilon 0 A over D, and the voltage on the capacitor is nothing but the electric field between the plates times D. So if we square this, we get the energy, right? So you have D squared here, you have D here, they are going to cancel out, and we are going to end up with 1/2 epsilon 0, the square of the electric field between them, times A times D. But now my question to you is, what is A times D? A, remember, is the area of these plates, and the D is the distance between them, which basically is going to give us the volume between the plates of the capacitor. So if you are interested in the energy density, then it's going to be, let's write this with lowercase u divided by the volume, which is going to be, obviously now if you divide it by volume, you are going to get 1/2 epsilon 0 E squared. So this is the energy density of the energy stored between the plates of the capacitor. So what this result is suggesting is that the energy is actually stored in the electric field between the capacitor plates. So even though we derive this expression for a parallel plate capacitor, this is true for any region where there is electric field. So you don't need to have any conductors, any charges around. If there is any electric field in a region of space, we say that there is energy there stored in the electric field, where the energy density is 1/2 epsilon 0 E squared. Let's end this video with an example. We all know electromagnetic waves and how they carry energy. And actually the energy carried by electromagnetic waves is stored in electric and the magnetic fields that makes it up. Now, in the upcoming chapters, we are going to talk about magnetic field and how the energy is also stored in magnetic field, and the energy density for the magnetic field is also of the same form, which is some constant times the magnetic field squared, which you are going to see in more detail. So with this, we conclude our video lecture. You guys stay healthy. Have a nice day, and we will talk to you later.